You've seen it a million times, right? An icy street, a salt truck rolls by, and just like that, the ice starts to disappear. It feels like a simple little trick, but the science behind it, well, it's incredibly powerful, and it does a lot more than just clear our winter roads.
So let's just get right to it. Why salt? I mean, why not sand? Or, I don't know, sugar? The answer has nothing to do with salt being salty. It's actually all about a fascinating principle in chemistry that's basically just a big numbers game.
And that principle is called a colligative property. Now I know, that sounds super technical, but the idea is actually really simple. It means that certain properties of a liquid change based on how many little things you dissolve in it, not what those things are. It's all about quantity over quality.
And to really get a grip on this numbers game, you gotta meet the star of the show, the Van Hoff factor. We just call it I. Think of it as a secret multiplier. It tells us exactly how many pieces a substance breaks into when you dissolve it. It's the key to the whole thing.
Okay, check this out. This is why that I factor is such a big deal. When something dissolves, it's not always a one-for-one deal. So you take something like methanol, a non-electrolyte. You put one molecule in, you get one particle out. Its I factor is just 1. But then you look at our road salt, sodium chloride. It's an electrolyte. One little unit of salt breaks apart into 2 ions, a sodium and a chloride. Boom! Its I factor is 2. It literally doubles its power. And you can see some compounds can even triple or quadruple it.
So, the most important rule to remember through all of this is super simple. The more particles you can cram into a solution, the bigger the effect you're going to get. It's that direct. More particles, more power.
All right, so what are the consequences of adding all these particles? Well, the first big one is that you literally stretch the temperature range where water can stay a liquid. You're making it harder for it to freeze and at the same time harder for it to boil.
And this shows you exactly how that works. On one hand, you have freezing point depression. That means the water now has to get even colder than usual to turn into ice. And on the other hand, you have boiling point elevation. It has to get hotter than usual to turn into steam. The particles are basically pushing those two boundaries further and further apart.
So why does the freezing point drop? Well, think about it like this. For water to freeze, all its molecules have to line up in this perfect, orderly crystal structure. But our little salt particles, they get in the way. They're like these chaotic guests at a super organized party, just bumping into everyone and preventing them from getting into formation. So to overcome all that chaos, the whole system has to get even colder before it can finally lock into place.
Now that's a pretty good explanation, right? But let's actually prove it. Let's see just how much of a difference that particle doubling effect from salt really makes in the real world.
Okay, don't worry about the formula itself. Just look at the pieces. See that I? That's our hero, the Van Hoff factor. And we know for salts, it's 2. The other numbers are just a constant for water and how much salt we added. So you plug it all in, and what do you get? The freezing point changes by negative 3.72 degrees Celsius. And there it is. That's the answer to our original question. Water normally freezes at 0 degrees Celsius, right? Well, we just slammed that freezing point all the way down to almost minus 4 Celsius. So if it's, say, minus 2 degrees outside, the ice on the road is now warmer than its new freezing point. It has to melt. It's simple, it's powerful, and it works.
All right, so freezing makes total sense. But what about boiling? Why does the boiling point go up? Now, you might have heard some explanation about intermolecular forces, but honestly, that's not really the whole story. The real reason is, well, it's a lot cooler.
The real reason is actually about stability. See, pure water is kind of restless. Its molecules are always ready to escape and become a gas. But when you dissolve salt in it, the water molecules get busy interacting with all those salt ions. It actually calms them down, making the whole liquid phase more stable. It's at a lower energy level. So to get those now chilled out water molecules to boil, you have to pump in way more energy, way more heat, to get them excited enough to escape. And more heat means a higher temperature.
So, we've seen how these particles can mess with temperature, but that's not all they do. Their power also lets them control another fundamental force, pressure. And it all comes from that same basic idea of just getting in the way.
First up is vapor pressure. You can think of vapor pressure as let's say, the desire of water molecules to escape into the air. When you add salt, some of those salt particles just hang out right at the surface, and they physically block the water from leaving. It's like having bouncers at the exit. Fewer molecules escaping means a lower pressure building up above the liquid. Now, this idea of concentration is absolutely key for our next topic, osmosis. And the trick is to stop thinking about the salt and start thinking from the water's point of view. Where there's very little salt, there's a high concentration of water. And where there's a ton of salt, there's a low concentration of water.
And, nature just loves to find balance. So if you separate these two solutions with a special filter that only lets water through, the water is going to move all by itself. It's going to flow from the side where there's a lot of water to the side where there isn't as much, trying to even things out. That's it. That's osmosis.
And this natural flow, it's not a gentle thing. It's a powerful force, creating a real physical pressure. And we can measure it. The amount of pressure you'd have to apply to push back and stop that flow completely, that's what we call osmotic pressure. It's basically a measure of how badly the water wants to move. So, just how powerful is this force? For that same saltwater solution we've been talking about, the osmotic pressure is an incredible 48.9 atmospheres. Let me put that in perspective for you. That is almost 50 times the normal air pressure we're all feeling right now. This is not some small, subtle effect. It's a massive force of nature created just by dissolving some salt in water.
And this huge pressure, this is where our whole story comes together, leading to one of the most important technologies we have today, getting fresh, clean drinking water from the ocean. This leads to a really brilliant question. We know what osmotic pressure is. It's the force needed just to stop water's natural flow. So what if we fight back? What if we push against it with even more pressure than that huge 48.9 atmospheres?
Well, when you do that, you overwhelm nature's tendency. You force the water to flow completely backwards in the opposite direction of osmosis. The pure water molecules get squeezed through the filter, away from the salty side, leaving all the salt particles behind. And this beautiful, elegant process, that's called reverse osmosis. It's how we desalinate seawater all over the world.
So let's just recap the big takeaways here. First, it's all about the numbers. It doesn't matter what the particle is, just how many there are. Second, that Van 't Hoff factor, that I, is the secret key that tells you how much power you're going to get. And finally, this one simple principle has mind-blowing real-world applications, from something as simple as melting ice to something as critical as making fresh water.
And that kind of leaves us with one last thing to think about. We've seen how just the sheer number of things can totally change the physical world. It really makes you wonder, what other systems out there, maybe in science or economics, or even in our own lives, are secretly being controlled not by what the pieces are, but simply by how many of them there are?